Picture the night sky, countless stars twinkling in an endless sea of darkness. But what if I told you that between those stars, there's something even more mysterious than the stars themselves? A vast, invisible ocean of gas and dust, stretching across unimaginable distances, holding secrets that challenge everything we think we know about the universe. This is the interstellar medium, the shadowy fabric of space, whispering tales of cosmic puzzles we're only beginning to unravel. Think about the last time you looked up and felt small under the weight of the cosmos. That feeling, it's just the tip of the iceberg, because hidden in the void between stars are mysteries so profound, they make black holes look straightforward. We're talking about forces that sculpt galaxies, particles moving at impossible speeds, and clouds of matter so strange they shouldn't exist under the laws of physics as we understand them. And yet, here they are waiting for us to decode their riddles, so buckle up. Over the next 30 mysteries, we're diving headfirst into the unexplained. From ghostly radio signals with no known source to bizarre molecules that shouldn't survive in the vacuum of space, each discovery pulls back another layer of this cosmic enigma. By the end, you'll see the night sky differently, not just as a blanket of stars, but as a living, breathing frontier, teeming with questions begging to be answered. Ready to explore? Let's begin. Our first stop in this cosmic journey takes us to the very edge of our solar system, where the sun's influence abruptly ends and the wild unknown of interstellar space begins. This boundary, called the heliopause, isn't just a quiet handoff. It's a chaotic frontier where the solar wind, a stream of charged particles racing outward from the sun, collides head-on with the interstellar medium. Scientists expected this transition to be smooth, but when the Voyager probes crossed this threshold, they sent back data that left researchers scratching their heads. Instead of a gradual fade, the probes encountered something far stranger. An invisible barrier, almost like a cosmic fence, where particle densities spiked and magnetic fields twisted in ways no one predicted. One theory suggests this turbulence comes from magnetic bubbles, vast, roiling structures created as the sun's magnetic field tangles with interstellar forces. Picture two rivers crashing together, their currents swirling into whirlpools. Now imagine that happening across millions of miles, with forces so powerful they deflect particles like a shield. Another idea points to pressure from the interstellar medium itself, like an invisible wind piling up against the solar wind, compressing it into this strange, dense boundary layer. But here's the kicker: our models of how these forces interact don't fully explain what Voyager saw. It's as if we're missing a piece of the puzzle, something fundamental about how space itself behaves at these unimaginable scales. And that's what makes this mystery so thrilling. The heliopause isn't just a line on a diagram, it's a dynamic, ever-shifting zone where the rules we thought we knew might not apply. Every new piece of data forces us to rethink our assumptions. Could there be undiscovered physics at play? Or is this just the first hint of a much larger tapestry of cosmic interactions we've yet to unravel? One thing's for sure, the answers won't just rewrite textbooks, they'll redefine how we see our place in the galaxy. The interstellar medium isn't just empty space, it's a cosmic sponge, a vast, frothy labyrinth of bubbles and filaments stretching across the galaxy. Scientists call this structure the galactic foam, and it's one of the most bewildering features of our universe. Imagine pouring champagne into a glass, watching those effervescent bubbles rise and pop, except here, the bubbles are light years wide, and instead of champagne, they're sculpted by the violent deaths of stars. Supernovae are the primary architects of this foam. When a massive star explodes, it blasts out shock waves that plow through the surrounding gas, carving enormous cavities. Stellar winds from young, energetic stars also contribute, pushing against the interstellar medium like cosmic snowplows. Over time, these forces create a tangled web of empty voids and dense filament structures so intricate they resemble the froth on a cappuccino. Yet, when astronomers map these regions using radio telescopes, they find something even stranger. Some bubbles are too perfectly spherical, as if shaped by an unseen hand, while others cluster in patterns that defy our understanding of turbulence and pressure. One of the biggest puzzles is how these structures remain so well defined over millions of years. Normally, gas in space should dissipate, spreading out until it blends into the background. But the galactic foam defies that expectation. Its walls stay sharp, and its bubbles refuse to pop. Some researchers speculate that magnetic fields act like invisible scaffolds, holding everything in place. Others think there's a hidden interplay of forces, something beyond just supernova and stellar winds, that keeps this cosmic froth stable. Then there are the forbidden zones, regions where the foam's structure contradicts the known laws of physics. In certain patches, gas densities fluctuate in ways that shouldn't be possible, like a stormy ocean suddenly freezing mid-wave without explanation. Could dark matter be influencing these anomalies? Or is there an undiscovered energy source at work? The more we study this foamy labyrinth, the more questions arise. What's remarkable is that this chaotic foam isn't random, it's organized. Observations reveal that galaxies with active star formation have more pronounced foam-like structures, almost as if this froth is a cosmic blueprint for stellar nurseries. It's as though the universe itself is playing a game of connect the dots, using these bubbles and filaments to guide the birth of new stars. So why does this matter? Because the galactic foam isn't just a curiosity, it's a key to understanding how galaxies evolve. If we can decode why these structures exist and how they persist, we might unlock secrets about the life cycles of stars, the distribution of matter, and even the fate of our own Milky Way. For now, though, it remains a masterpiece written in gas, dust, and unanswered questions, one of the Interstellar Medium's most captivating enigmas. Now let's tackle one of the most frustrating gaps in our cosmic understanding: the case of the universe's missing ordinary matter. Scientists call this the missing baryon problem, and it's as perplexing as walking into a room where half the furniture has mysteriously vanished. Baryons, the particles that make up everything we can see, from stars to planets to you and me, should account for about 5% of the universe's total content based on our best calculations. But when astronomers tally up all the visible matter in galaxies, gas clouds, and stellar objects, they come up short, way short. Nearly half the universe's expected ordinary matter is simply gone. Where could it be hiding? The leading suspect is an elusive form of matter called the warm-hot intergalactic medium, or WIM for short. Picture an invisible fog of superheated gas, thinner than the best laboratory vacuum, yet so vast it stretches between galaxies. This plasma is scorching, reaching temperatures of hundreds of thousands to millions of degrees, but it's so diffuse that current telescopes can barely glimpse it. Detecting WIM is like trying to spot a single glowing ember in a pitch-black forest. Why is this gas so hard to find? For one, it doesn't emit much visible light. It's too hot for atoms to hold onto their electrons normally, so they can't produce the familiar spectral lines our telescopes rely on. Instead, astronomers hunt for subtle absorption patterns in the X-ray light passing through space, looking for faint imprints of highly ionized oxygen and nitrogen. It's painstaking work. These signals are drowned out by brighter cosmic sources, like trying to hear a whisper at a rock concert. But here's where things get even weirder. Even accounting for WIM, there's still a gap. Some scientists speculate that part of the missing matter could be tied up in colossal, thread-like structures, cosmic rivers of plasma flowing along the scaffolding of dark matter filaments. Others wonder if ultra-diffuse clouds, too faint to register with our instruments, might be lurking unseen. There's even a radical theory suggesting some baryons might have been ejected into intergalactic space by supermassive black holes, flung so far they've effectively vanished from our observable reach. The stakes couldn't be higher. Solving this mystery isn't just about bookkeeping for the universe, it's about verifying whether our fundamental models of cosmic structure hold up. If we're missing something as basic as where ordinary matter resides, what else might we have wrong? Future telescopes like ESA's Athena X-ray Observatory could finally bring WIM into focus. But until then, those missing baryons remain one of the interstellar medium's most tantalizing riddles, a ghostly reminder that even in the vastness of space, the most important clues might be the ones we can't see. Deep within the interstellar medium, hidden behind veils of dust, lie some of the coldest and most enigmatic places in the cosmos' dark molecular clouds. These colossal structures, spanning dozens of light years, are cosmic nurseries where stars should be born in abundance. Yet some of these clouds defy expectations, remaining eerily quiet, their gas stubbornly refusing to collapse into new stars. It's as if the universe hit pause on creation itself, leaving astronomers puzzled over what's holding these clouds back. Take the famous Barnard 68, a dark cloud so dense it blocks out the stars behind it like an ink blot on the night sky. At first glance, it seems like the perfect cradle for star formation, freezing temperatures near absolute zero, thick with molecules like hydrogen and carbon monoxide. But instead of birthing stars, it sits there, almost dormant. Why? One clue lies in the delicate balance between gravity and other invisible forces at play. Gravity should pull the gas inward, compressing it until it ignites into new stars. But inside these clouds, magnetic fields weave through the gas like an intricate spiderweb, creating resistance. Think of it like trying to collapse a balloon filled with iron filings. The magnetic forces push back, counteracting gravity's pull. Chemistry adds another layer of mystery. These clouds aren't just empty voids, they're bustling with complex molecules, some containing dozens of atoms. In fact, scientists have detected everything from simple water molecules to organic compounds like formaldehyde and even sugar in space. These molecules don't just float passively, they interact, absorbing energy and radiating it away, which can cool the cloud further and prevent collapse. It's like a cosmic refrigeration cycle, keeping the gas just stable enough to resist stellar birth. Then there's turbulence, chaotic motions within the cloud that stir the gas like a spoon in a cosmic soup. In some regions, this turbulence can actually support the cloud against gravity, preventing it from condensing. Imagine shaking a snow globe so vigorously that the flakes never settle. That's turbulence at work in these dark clouds. Yet in other cases, turbulence can trigger star formation by creating dense pockets where gravity gains the upper hand. The line between stability and collapse is razor thin, and we still don't fully understand what tips the scales. Perhaps the most baffling aspect is the existence of starless cores, dense knots within these clouds that have all the right conditions for star formation but simply don't. It's like finding a loaded gun that never fires. Some theories suggest that external radiation from nearby stars might be pressurizing these cores, effectively putting them in a state of suspended animation. Others propose that slow, subtle processes like the gradual dissipation of magnetic fields might one day allow these clouds to awaken, but on timescales far longer than we've been observing them. What's at stake here isn't just a curiosity about star formation, it's about understanding the very rhythm of the cosmos. If we can unravel why some clouds resist collapse, we might unlock secrets about how galaxies regulate their star-forming factories. Are these dark clouds cosmic hoarders, saving their gas for some future burst of creation? Or are they evidence of forces we haven't yet discovered, quietly shaping the universe in ways we're only beginning to glimpse? For now, these silent giants remain one of the interstellar medium's most profound puzzles, reminding us that even in the darkest corners of space, the universe holds its secrets close. Starlight carries more than just brightness across the cosmos. It brings clues hidden in its very fabric, clues that have baffled scientists for over 100 years. When astronomers split the light from distant stars into its component colors, they sometimes find dark lines where specific wavelengths have been mysteriously absorbed. Some of these lines match known elements like hydrogen or helium, but then there are the others, hundreds of unexplained stripes in the spectrum known as the diffuse interstellar bands or DIB. These aren't just random blips, they're consistent, showing up in nearly every direction we look, as if the universe is whispering a code we haven't cracked. The leading suspect, enormous complex molecules drifting between the stars, specifically polycyclic aromatic hydrocarbons or par-carbon-based compounds shaped like tiny hexagons linked together in sheets. They're sturdy, they're abundant, and they can absorb light in ways that might explain some of those mysterious bands. But here's the catch: no matter how hard scientists try, they can't recreate the exact DIB signatures in labs. It's like having a fingerprint from a crime scene but no suspect whose fingers match. Then there's the quantum twist. Some researchers argue these bands might not come from molecules at all, but from exotic quantum effects within interstellar dust grains, tiny solid particles floating in space. Picture an electron trapped inside a microscopic cage, jumping between energy levels in ways we've never observed on Earth. If true, this would mean there's an entirely new layer of physics at play in the cold, dark reaches between stars. The real head-scratcher is why these bands are so diffuse. If they were caused by specific molecules, we'd expect them to show up sharply at certain wavelengths. Instead, they're smeared out as if something is blurring the cosmic fingerprint. Could it be that these molecules are being distorted by the extreme conditions of space, twisting in ways that alter their light absorption properties? Or are we seeing the combined effect of countless different compounds, each contributing a tiny piece to the puzzle? One thing's certain: solving the mystery of the diffuse interstellar bands isn't just about filling in a gap in our spectral charts. It's about understanding the very ingredients floating between the stars' ingredients that might hold the building blocks of life itself. If these bands come from complex organic molecules, it would mean the universe is peppered with the raw materials for biology long before planets even form. But if they're signs of new physics, it could reshape our understanding of how matter behaves in the most alien environments imaginable. For now, the diffuse interstellar bands remain one of the most persistent enigmas in astronomy. They're a reminder that even when we stare directly at the evidence light streaming from stars, filtered through the vastness of space, the universe still finds ways to keep its deepest secrets just out of reach. Look closely at the night sky, and you'll notice something beyond the stars' dark patches where the Milky Way's glow dims dramatically. This isn't empty space. It's the work of interstellar dust, tiny particles so pervasive they shape our view of the cosmos. But calling them dust sells them short. These aren't just specks of dirt, they're sophisticated cosmic architects, sculpting light, birthing molecules, and hiding secrets about their own origins that scientists are still racing to decode. For starters, their size defies intuition. While we imagine dust as fine powder, interstellar grains range wildly from smaller than a virus to the width of a human hair. Some are fluffy, with structures so porous they resemble cosmic snowflakes. Others are dense, like microscopic gemstones forged in stellar furnaces. Their shapes aren't uniform either. Certain grains align like compass needles along magnetic fields, polarizing starlight in ways that reveal hidden forces threading through the galaxy. Then there's their composition, a cocktail of elements that reads like a mad scientist's experiment. Silicates, carbon, and even frozen ices cling to their surfaces. But the real shock came when astronomers found organic molecules and prebiotic compounds clinging to these grains. Picture this: tiny, frozen mantles of water, methanol, and ammonia coating specks of carbon drifting between stars. Under the right conditions, these ices can undergo chemical reactions, assembling complex molecules like formaldehyde or acetic acid, ingredients essential for life. It's as if the universe is running chemistry experiments on a galactic scale, with dust grains as its microscopic lab benches. Yet for all their importance, we still don't fully know where these grains come from. Supernovas seem like obvious factories, violent explosions that blast material outward, cooling into solid particles. But there's a problem. Models suggest supernova dust should be destroyed by subsequent shockwaves before it can spread far. On the flip side, red giants and asymptotic giant branch stars expel gentle stellar winds rich in carbon and silicates, seeding space with fresh dust, but observations show they can't account for all the dust we see. The plot thickens when you consider dust's uneven distribution. In some regions, like the pillars of creation, dust piles up in dense veils, blocking nearly all visible light. Elsewhere, it's suspiciously sparse. Why? One theory points to dust destruction zones around hot young stars, whose intense radiation evaporates nearby grains. Another suggests microscopic shrapnel from cosmic ray impacts might shatter dust particles over time. There's even evidence that some dust is recycled, eaten by star-forming clouds, and later expelled anew like cosmic phoenix ashes. Perhaps the most tantalizing clue lies in presolar grains, tiny mineral fragments trapped in meteorites that predate our solar system. Analyzing these time capsules reveals isotopic signatures matching specific types of stars, proving some dust is truly ancient. But even these grains raise questions. Certain isotopic ratios don't match any known stellar source, hinting at exotic origins, maybe even from environments we've yet to discover. What's clear is that interstellar dust isn't just a backdrop, it's an active player in the cosmos, shaping how galaxies evolve and possibly seeding the chemistry for life itself. Yet every answer we uncover about these enigmatic particles seems to sprout three new questions. Are we looking at the remnants of dead stars, the waste products of cosmic chemistry, or something far stranger? Until we solve the riddle of their birth, the universe's dust will keep its origins shrouded in shadow, literally and figuratively. We live inside a cosmic anomaly, a vast, nearly empty sphere stretching 300 light-years in every direction, known as the local bubble. Picture a soap bubble floating in the air, but instead of soap film, this one's walls are made of glowing gas and starlight, and instead of air inside, there's an eerie void with just a whisper of matter. This isn't some random emptiness, it's a scar left by ancient violence, a cavity carved out by a series of supernova explosions that rocked our galactic neighborhood millions of years ago. What's bizarre is just how empty it is. Normally, interstellar space has about 1 atom per cubic centimeter, already a vacuum better than anything we can create on Earth. But inside the local bubble, that number drops to a mere tenth of an atom. That's like taking a single grain of sand and dispersing it across an entire football field. Even stranger, this ultra-diffuse environment isn't uniform. Patchy clouds of slightly denser gas drift through the void like ghosts, their origins still unclear. Scientists call these fluff structures, and they might hold clues to how the bubble evolved over time. But here's the real puzzle: how does this emptiness affect us? For one, it shapes the cosmic rays bombarding our solar system. These high-energy particles, flung across the galaxy by black holes and exploding stars, usually get slowed or deflected by denser interstellar gas. Inside our bubble, though, there's less to stop them. Some researchers think this might explain why certain isotopes on Earth, like iron-60, appear in higher concentrations than expected. Traces of an ancient cosmic ray surge when the bubble was younger and more turbulent. Then there's the bubble's transparency. With so little gas and dust to block light, we have an unusually clear view of surrounding stars and structures. Imagine living in a house with glass walls. You can see distant landscapes with startling clarity. That's the astronomical advantage our bubble provides. But it also distorts our perspective. Because we're sitting inside this void, it's easy to assume the rest of the universe looks the same, when in reality, most of the galaxy is far more crowded with gas and dust. Perhaps the biggest mystery is the bubble's lifespan. Supernova blasts create cavities, but over time, interstellar pressure should collapse them. Our bubble, however, has stayed inflated for millions of years, far longer than simple models predict. Some theories suggest magnetic fields act like internal scaffolding, propping it open. Others propose that a steady trickle of energy from nearby stellar winds or even dark matter interactions might be quietly keeping the void from imploding. What's certain is that the local bubble isn't just a passive backdrop. It's a dynamic, evolving structure that influences everything from the radiation bathing our planet to the way we perceive the cosmos. And as our solar system drifts toward one of its gauzy walls, we might soon find ourselves stepping into a very different interstellar environment, one that could rewrite what we know about our place in the galaxy. For now, though, this immense near-nothingness remains one of the interstellar medium's most quietly profound enigmas. At the edge of our solar system, where the sun's influence wanes and interstellar space begins, astronomers have stumbled upon something haunting: faint, whispering walls of hydrogen gas draped like ghostly curtains in the void. These structures, detected by their faint radio emissions, don't behave like ordinary cosmic debris. They're razor-thin, stretching for billions of miles, yet so diffuse they're nearly transparent. Some cling to the heliopause while others drift further out, as if marking invisible boundaries between stellar territories. What makes these hydrogen walls so baffling is their origin. One leading theory suggests they're cosmic fingerprints, leftover material from the solar system's birth, frozen in place like a fossilized breath. When the sun and planets formed, they emerged from a swirling cloud of gas and dust. Most of it was either pulled into the newborn star or blown away by the infant sun's violent winds, but traces might have lingered, pushed to the fringes and preserved in these delicate sheets. If true, studying these walls could be like reading a diary from the solar system's earliest days, written in atoms older than Earth itself. There's another, more dynamic possibility. These walls could be collision scars. As the sun hurtles through the galaxy, it doesn't travel through total emptiness. The interstellar medium is patchy, with ribbons of denser gas drifting like cosmic fog. When the solar wind, a stream of charged particles rushing outward from the sun, slams into these interstellar currents, it might compress the hydrogen ahead of it, piling it up into these faint barriers. Think of it like a ship's bow wave, but on an unimaginable scale, with forces so subtle they've taken decades to detect. But here's where things get truly strange. Some of these walls don't align with where they should be. Models predict they'd form a rough bubble around the solar system, shaped by the sun's motion. Instead, they're asymmetrical, warped, even twisted in ways that defy simple explanations. Could unseen magnetic fields be sculpting them, or are we seeing the aftermath of a long-forgotten stellar encounter, a close brush with another star that stirred the gas like a spoon in tea? The real challenge lies in studying them. Hydrogen walls don't emit light. They reveal themselves only through the faintest radio whispers, a specific wavelength called the 21-centimeter line. Even then, Earth's own radio noise drowns out much of the signal. It took decades of refining telescope technology just to confirm these structures exist, and even now, their details blur like a half-remembered dream. Yet the stakes couldn't be higher. If these walls are primordial, they're time capsules holding clues to how solar systems like ours take shape. If they're dynamic, shaped by the interstellar medium, they're proof of an ongoing conversation between stars and the space between them, a dialogue we're only beginning to decipher. Either way, these whispering hydrogen walls are more than cosmic curiosities. They're silent witnesses to forces that shaped our past and may yet shape our future as the solar system continues its eternal voyage through the galaxy's unseen currents. Starlight doesn't travel through the cosmos unscathed. By the time it reaches our telescopes, it often carries a hidden fingerprint of its journey. One of the most peculiar clues is polarization, a subtle twisting of light waves that reveals secrets about the interstellar medium. Normally, light vibrates in all directions, but when it passes through clouds of cosmic dust, something extraordinary happens. The dust grains, shaped like microscopic needles, align themselves along magnetic fields like compasses pointing north. As light travels past them, these grains preferentially absorb and scatter light vibrating in certain directions, leaving the remaining light polarized, a phenomenon that should, in theory, map out the Milky Way's magnetic fields with precision. Yet when astronomers measure this polarization across the galaxy, they find inconsistencies that defy expectations. Some regions show polarization so strong it suggests magnetic fields far more intense than our models predict. Other areas display bizarre, swirling patterns like fingerprints smudged by an unseen hand where the dust grains seem to align in ways that shouldn't be possible under known physics. It's as if the universe is hiding a second layer of magnetism, one we haven't yet learned to detect. Take the Taurus molecular cloud, a stellar nursery just 450 light-years away. Here, dust polarization paints a magnetic field that coils through the gas like a serpent, contradicting the relatively orderly fields we see elsewhere. One explanation points to turbulence. Chaotic motions within the cloud could twist the magnetic lines into knots, but simulations struggle to recreate the observed patterns, leaving scientists to wonder if there's an unknown force at work, perhaps linked to the way interstellar dust interacts with these fields on a quantum level. Even stranger are the null points, areas where polarization suddenly vanishes, as if the dust grains forgot which way to align. At first glance, this might suggest a simple absence of magnetism. But that's impossible. We know magnetic fields permeate every corner of the galaxy. Instead, researchers suspect these nulls might mark zones where multiple magnetic fields collide and cancel each other out, like waves crashing together in perfect opposition. Alternatively, the dust grains themselves might be behaving unusually, perhaps coated in ices that alter their magnetic properties or tumbling erratically due to impacts with rogue atoms. The stakes of this mystery stretch beyond mere curiosity. Polarized starlight isn't just a curiosity, it's a critical tool for understanding how galaxies evolve. Magnetic fields regulate star formation, govern the flow of cosmic rays, and even shape the spiral arms of galaxies like our Milky Way. If our maps of these fields are incomplete, we might be missing a fundamental piece of how the universe structures itself. Future telescopes like the upcoming LightBird mission aim to measure polarization with unprecedented precision, potentially unveiling hidden magnetic phenomena. Until then, the polarization puzzle stands as a humbling reminder. Even something as seemingly straightforward as starlight carries layers of cosmic intrigue, and the interstellar medium still has a few tricks up its sleeve. Every flicker of polarized light is both a clue and a question, one that might rewrite our understanding of the forces weaving through the darkness between the stars. In the vast blackness between stars, an eerie glow persists, one that defies all expectations. Astronomers call it the unidentified infrared emission, and it's as baffling as stumbling upon a lit candle in the middle of a desert. Across the galaxy, telescopes detect faint infrared light radiating at specific wavelengths, but here's the catch. No known cosmic material should produce this exact pattern. It's like hearing a song where every note is recognizable, yet the melody itself is utterly alien. The leading suspects, microscopic diamonds, not the glittering gems you'd find in jewelry, but nanodiamonds, carbon crystals smaller than a virus, forged in the hearts of dying stars or the shockwaves of supernovae. These tiny structures have a unique ability to vibrate when struck by starlight, emitting infrared radiation at distinct frequencies. Some regions, like the protoplanetary disk around the young star HD 970,377, show infrared signatures that match lab-created nanodiamonds almost perfectly. But there's a snag. The cosmic versions emit more light than their earthly counterparts, as if they're being turbocharged by some unseen force in space. Then there's the polycyclic aromatic hydrocarbon theory, complex carbon molecules shaped like chicken wire, which also radiate in the infrared. These PAHs are everywhere, from comet tails to distant nebulae, and they're excellent at absorbing starlight and re-emitting it at longer wavelengths. Yet when scientists compare the observed emissions to pH spectra, the match is close but not perfect. It's as though the interstellar medium is working with a variant of these molecules that doesn't exist in any lab. The plot thickens when you consider the orphan emissions, infrared signals that don't align with any known carbon structure. In the reflection nebula Messier 17, for example, telescopes have spotted mysterious bands of infrared light that resist all attempts at identification. Some researchers speculate these could come from entirely new forms of carbon, perhaps exotic cage-like molecules or graphene flakes vibrating in ways we've never observed. Others wonder if quantum effects in interstellar dust grains might be at play, with electrons trapped in peculiar energy states emitting light as they jump between levels. Perhaps the most tantalizing clue lies in the distribution of this glow. It's not uniform. Some of the brightest emissions come from regions where stars are forming, suggesting a connection to young stellar objects. But other patches appear in seemingly empty space, far from any obvious energy source. Could there be an interstellar dark web of carbon-rich material, quietly processing starlight into these enigmatic emissions? Or are we seeing the collective glow of countless microscopic processes, each too faint to detect individually but overwhelming in aggregate? What's clear is that this ghostly infrared light isn't just a curiosity, it's a breadcrumb trail leading to deeper mysteries about how carbon, the foundation of life, behaves in the cosmic wild. If nanodiamonds are truly responsible, their abundance would rewrite our understanding of how materials disperse across galaxies. If it's something else entirely, we may be on the verge of discovering a new chapter in interstellar chemistry. For now, the unidentified infrared emission remains a luminous riddle, reminding us that even in the darkness of space, there are whispers of light we're only beginning to decode. Between galaxies, in what seems like empty darkness, the cosmos hides an intricate network of highways, vast filaments of gas stretching millions of light years, weaving the universe together like threads in a cosmic tapestry. This is the cosmic web, the scaffolding upon which galaxies are built, and yet some of its most critical structures remain nearly invisible to us. These hidden threads, composed mostly of ionized hydrogen and dark matter, should be the universe's most obvious freeways, funneling gas into galaxies and fueling star birth. But when astronomers try to map them, they keep running into the same problem where the models predict bright, glowing strands. They often find only ghostly wisps or nothing at all. One of the biggest surprises came when scientists pointed telescopes at the space between galaxy clusters, expecting to see filaments glowing with hot gas. Instead, many appeared far dimmer than simulations suggested, as if something had siphoned away their energy. Some filaments even seemed to vanish entirely, detectable only by the way their gravity subtly bends passing light. The leading theory, the gas might be cooling faster than expected, condensing into clumps too faint to spot. It's like expecting a neon sign and finding only a dying ember. But here's where the mystery deepens. Even the filaments we can detect don't behave the way they should. Take the cosmic necklace near the galaxy cluster Able 2028, a string of glowing gas blobs, each a galactic nursery, strung along a dark matter filament like pearls. The blobs are too massive, too bright, and spaced too evenly for standard models to explain. It's as if an unseen hand arranged them deliberately. Some researchers suggest magnetic fields might be shaping these structures, squeezing gas into these precise formations. Others propose that turbulence in the early universe left behind ripples that now dictate where gas accumulates. Then there's the feeding problem. Galaxies need a steady supply of gas to form stars, yet many filaments seem to deliver that gas too slowly or not at all. In some cases, gas appears to stall just outside galaxies, as if hitting an invisible barrier. Could galactic magnetic fields be pushing back, or are we underestimating how much gas slips in as cold, invisible streams, sneaking past our telescopes undetected? The answer matters more than you'd think. Without these threads feeding them, galaxies would starve, and the universe as we know it wouldn't exist. The most tantalizing clue might come from the filaments we can't see, the so-called dark filaments. These are threads so diffuse or so uniformly spread they absorb and emit almost no light. Some might be cloaked in dark matter, their gravity the only hint of their presence. Others could be made of primordial gas, untouched since the dawn of time, lurking like cosmic fossils. A few daring theories even suggest these dark threads might be conduits for exotic particles or unknown forces, subtly influencing galaxy growth in ways we've yet to comprehend. What's at stake here isn't just a puzzle about gas distribution, it's a question about the universe's blueprint. If filaments are fainter or more erratic than our models predict, it could mean we're missing a fundamental piece of how structure forms in the cosmos. Are we underestimating the role of turbulence, overlooking the impact of dark matter? Or is there something entirely new at work, a hidden rule in the universe's playbook that's been quietly shaping galaxies all along? Until we solve the riddle of these hidden threads, the cosmic web will remain one of the interstellar medium's most profound and elusive mysteries. Buried deep in Earth's ocean floors lies a radioactive whisper from the cosmos, Iron-60, an isotope so rare it shouldn't exist naturally on our planet. This isn't some terrestrial oddity, it's stardust forged in the heart of a dying star and flung across space to settle in the sediments beneath our seas. When scientists first discovered traces of Iron-60 in deep sea cores, it sent shockwaves through the astronomy community. Here was concrete proof that Earth had been dusted by debris from ancient supernova explosions so powerful they left their mark on our world millions of years after the fact. But the plot thickens when you look at the distribution. Instead of a smooth layer of Iron-60 blanketing the globe, the isotope appears in bizarre, uneven patches, some sediment layers rich with it, others completely devoid. It's as if the universe flicked bits of radioactive confetti at Earth, leaving some areas drenched while others stayed dry. One explanation points to the chaotic nature of supernova debris clouds. When a star explodes, it doesn't eject material evenly in all directions. It's more like a shotgun blast with clumps of matter hurtling outward at different speeds. If one of those clumps happened to cross paths with Earth, it might explain the patchiness. Then there's the travel mystery. Iron-60 is heavy and space is vast. For it to reach us, it needed a cosmic delivery system. Some researchers argue that the local bubble, that eerily empty region surrounding our solar system, might hold the key. Supernova that carved out this bubble could have also ejected Iron-60, riding shock waves like interstellar surfboards until they crashed into Earth's atmosphere. Others propose a more controversial idea, that the isotope hitched a ride inside micrometeorites or interstellar dust grains, shielded from degradation by their protective shells. The timeline adds another layer of intrigue. Iron-60 has a half-life of 2.6 million years, meaning the deposits we find must have arrived relatively recently in cosmic terms, likely within the last 10 million years. Geological evidence points to at least two major influxes, one around 2.7 million years ago, another roughly 7 million years back. Both coincide with periods of climatic upheaval on Earth, sparking wild theories about supernova triggering ice ages or even influencing evolution. But here's the catch: Iron-60 alone isn't energetic enough to cause such disruptions. So if these stellar explosions did affect Earth, how? The leading hypothesis involves cosmic rays. A nearby supernova wouldn't just sprinkle Iron-60 on us, it would bathe the solar system in high-energy particles, potentially altering atmospheric chemistry or cloud formation. Some studies suggest these rays could have increased mutation rates in organisms, subtly steering life's trajectory. It's a staggering thought that events half a galaxy away might have nudged the course of biology right here on Earth. Yet for all the tantalizing clues, Iron 60's story remains incomplete. Why do some ocean sediments show spikes in concentration while nearby samples show nothing? Did multiple supernovae contribute, or did a single explosion's debris reach us in waves? And most perplexing of all, how much of this interstellar visitor still lies undetected, hidden in unexplored corners of our planet's geological record? Every new core sample holds the potential to rewrite this radioactive mystery, reminding us that Earth isn't just a solitary world. It's a cosmic traveler carrying fragments of distant cataclysms in its very bones. Lithium should be everywhere in the universe, literally. According to our best models of the Big Bang, this lightweight element was forged in abundance during the universe's first few minutes alongside hydrogen and helium. Yet when astronomers measure lithium levels in the interstellar medium, they find only a fraction of what those calculations predict. It's like baking a cake with 3 eggs, only to open the box later and find just 1. So where did all that lithium go? One possible culprit: stars. These cosmic furnaces are notoriously bad at preserving lithium. Inside a star's searing core, temperatures reach millions of degrees, hot enough to tear lithium atoms apart in a process called proton capture. But here's the catch: this destruction shouldn't account for all the missing lithium. Even accounting for stars devouring it, there's still a glaring deficit. Take young, metal-poor stars in the Milky Way's halo, for example. These ancient relics, born from nearly pristine Big Bang material, should be lithium-rich. Instead, their lithium levels are mysteriously uniform, and about 3 times lower than primordial predictions, as if some universal balancing act erased the excess without leaving a trace. Then there's the interstellar medium itself. Could lithium be hiding in plain sight, camouflaged within gas clouds? Normally, we'd detect it through its spectral fingerprints, specific wavelengths of light it absorbs or emits. But lithium is sneaky. Unlike hydrogen or helium, it's easily ionized, stripped of its electrons by ambient starlight. In this charged state, it becomes nearly invisible to optical telescopes. Some researchers speculate that vast reservoirs of ionized lithium might lurk in warm, diffuse gas clouds, evading detection because we've been looking for the wrong signals. But the plot thickens when you consider cosmic rays. High-energy particles zipping through space can smash into heavier atoms like carbon or oxygen, shattering them into fragments, including lithium. This process, called spallation, should be producing extra lithium over time, not reducing it. Yet somehow, the interstellar medium's lithium budget remains stubbornly in the red. It's as if the universe has a hidden lithium disposal system, scrubbing it away faster than natural processes can replenish it. Perhaps the boldest theory involves undiscovered physics. What if our understanding of Big Bang nucleosynthesis is incomplete? The calculations predicting lithium abundance rely on precise nuclear reaction rates, values we've measured in labs here on Earth. But what if those rates shift under extreme cosmic conditions? Some theorists propose exotic particles or unknown forces might have altered lithium production in the early universe, skewing the numbers. Others wonder if dark matter played a role, with hypothetical particles interacting in ways that suppressed lithium formation during those critical first minutes. For now, the lithium discrepancy remains one of the most persistent headaches in cosmology. It's a problem that straddles the line between stellar astrophysics and fundamental particle physics, challenging our models at every turn. Solving it won't just tell us where the missing lithium went. It might force us to rewrite the recipe for the universe's earliest moments. Until then, this lightweight element carries heavyweight questions, reminding us that even the simplest atoms can hold profound cosmic secrets. Galaxies aren't just static islands of stars, they're dynamic, breathing entities, and sometimes they exhale with unimaginable force. Picture this: colossal fountains of gas, some reaching tens of thousands of light years into space, erupting from galactic disks like geysers on a cosmic scale. These aren't gentle streams, they're titanic outflows, hurling entire oceans of material into the void, only for it to rain back down in a slow-motion cycle that shapes the fate of galaxies. Yet what's powering these eruptions remains one of the most heated debates in astrophysics. Take the Milky Way's own Fermi bubble's enormous lobes of hot gas stretching 25,000 light-years above and below our galaxy's core. They are the aftermath of a violent outburst, likely triggered by our supermassive black hole, Sagittarius, a star feasting on surrounding matter millions of years ago. But here's the puzzle: the energy required to launch gas that far defies even the most generous estimates of the black hole's past activity. It's like a firecracker somehow propelling a skyscraper into orbit. Some theorists argue that multiple smaller eruptions might have stacked up over time, while others propose an entirely different mechanism: cosmic winds driven by star formation in the galactic center, acting like a collective bellows. Then there's the mystery of recycling. These fountains don't just spit gas into oblivion, they're part of a galactic ecosystem. Observations of galaxies like Messier 82 reveal gas launched into the halo, cooling over millennia before falling back to replenish the disk, seeding new generations of stars. It's a self-sustaining cycle, except the numbers don't quite add up. Simulations struggle to explain how the returning gas retains enough mass and momentum to fuel future star birth. Some of it should dissipate, lost to intergalactic space, yet galaxies seem suspiciously efficient at recapturing their own exhaust. The real enigma lies in the smaller fountains, though. Dwarf galaxies, with their puny gravitational pull and scant energy reserves, shouldn't be capable of launching such outflows at all. Yet systems like NGC 1569 defy expectations, ejecting gas plumes that rival those of their giant cousins. One radical idea suggests that supernovae in these compact galaxies might be teaming up their combined explosions, creating overlapping shockwaves that act like a cosmic cannon. Another theory points to dark matter, whispering that its gravitational tinkering might be subtly aiding the process, though no one's quite sure how. What's clear is that these fountains are more than just cosmic spectacles, they're lifelines. Without them, galaxies would either choke on their own exhaust or bleed out their star-forming fuel too quickly. Yet every new observation deepens the mystery, revealing gaps in our understanding of how energy, matter, and gravity tango across these vast scales. Until we crack the code of what launches and sustains these galactic geysers, we're left staring up at the universe's version of Old Faithful, wondering what invisible hand is pulling the levers. Scanning the cosmos with radio telescopes, astronomers have long relied on carbon monoxide, or CO, as a trusted tracer for mapping hidden molecular gas. This molecule emits a distinctive signal, acting like a cosmic breadcrumb trail leading to vast star-forming clouds. But here's the unsettling truth: for every glowing CO cloud we detect, there's an invisible counterpart lurking in the shadows. These phantom reservoirs, nicknamed dark gas, don't play by the rules. They're rich in molecular hydrogen, the primary fuel for stars, yet they refuse to announce themselves through conventional surveys, leaving us blind to what could be a staggering fraction of the universe's building blocks. The first clues came from gamma rays. When high-energy particles collide with interstellar gas, they produce a telltale glow, and in certain regions, this gamma-ray signal hinted at dense molecular gas where CO was conspicuously absent. It's like stepping into a foggy forest and feeling damp air cling to your skin, even though your eyes see nothing but haze. Then came the dust maps. Cosmic dust, though faint, scatters and absorbs starlight in predictable ways. By studying these patterns, researchers realized some regions were far dustier than their CO emissions suggested, as if veiling unseen gas beneath. So what's hiding in these dark gas clouds? One possibility is that they're simply too cold. Carbon monoxide needs a bit of energy to emit detectable radiation, but if a gas cloud chills below a critical threshold, its CO goes silent. Another theory points to chemistry. In low metallicity environments, places starved of heavier elements, carbon and oxygen, might be too scarce to form much CO at all, leaving hydrogen molecules undetectable by standard methods. But the most tantalizing idea involves shielding. Thick layers of dust could be acting like a cosmic smokescreen, absorbing the very signals we rely on to see the gas behind them. The implications are staggering. If dark gas is as widespread as some studies suggest, we might be underestimating the mass of galaxies by as much as 30%. Imagine weighing a suitcase while unknowingly leaving half your clothes outside. That's the scale of error we're confronting. Star formation models would need recalibrating too. Young stars ignite where gas grows dense enough to collapse under gravity. But if large pockets of gas are invisible, our predictions about where and how stars are born could be fundamentally flawed. Perhaps the most haunting question is whether this dark gas could solve another cosmic riddle, the missing baryon problem. If these clouds are more abundant than we thought, they might account for a chunk of the universe's elusive ordinary matter. Future telescopes like the upcoming Square Kilometre Array could finally pierce the veil, hunting for the faint radio whispers of hydrogen molecules directly. Until then, these silent reservoirs remain ghosts in the interstellar machine, reminding us that even the emptiest corners of space might be far more crowded than they appear. Fluorine shouldn't be this controversial. It's the 19th most common element in your toothpaste, yet in the cosmos, it's a rebel appearing in unexpected pockets of space at levels that defy every model of how stars forge heavy elements. Astronomers call this the fluorine problem, and it's not just a quirk of chemistry. It's a cosmic whodunit with two prime suspects, the gentle winds of aging stars or the violent deaths of massive ones. The challenge: each leaves behind a forensic trail that doesn't quite match the crime scene. Take asymptotic giant branch stars, or AGB stars for short. These aging giants, bloated and luminous, were long considered fluorine factories. In their layered interiors, nuclear reactions fuse helium and hydrogen, creating just the right conditions to produce fluorine through a process called neutron capture. As these stars shed their outer layers, they're supposed to pepper the interstellar medium with fluorine-rich dust. Observations of some planetary nebulae, like the Helix Nebula, seem to support this. Yet when astronomers tally up the fluorine these stars should have spread across the galaxy, the numbers fall short, sometimes by a factor of 10. It's like baking cookies for a party and realizing you've mysteriously run out halfway through. Then there's the supernova theory. When massive stars explode, the shockwaves can trigger rapid neutron capture, the same process that creates gold and uranium. Fluorine, it turns out, might be a byproduct. In fact, gamma-ray telescopes have spotted fluorine isotopes in the remnants of supernova like Cassiopeia A, suggesting these violent events could be key suppliers. But here's the catch: supernova produce fluorine under such extreme conditions that most of it should get destroyed immediately after formation, like a sandcastle washed away by the tide. Yet somehow, inexplicably, we find it lingering in interstellar clouds. The distribution only deepens the riddle. Fluorine isn't sprinkled evenly across the galaxy. It clumps in hotspots like cosmic salt deposits. In star-forming regions like the Orion Nebula, it's surprisingly abundant, but in other areas, even those teeming with AGB stars, it's nearly absent. One theory suggests fluorine might be clinging to dust grains, surviving longer in certain environments before getting blasted apart by radiation. Another wild idea involves Wolf-Rayet stars, rare, ultra-hot giants that might forge fluorine in their ferocious winds before ejecting it into space like celestial confetti. What makes this mystery so urgent is fluorine's fragility. It's the lightest element that can't be made in the Big Bang, meaning every atom we see had to be forged in stars. Yet its survival hinges on perfect cosmic conditions. Too much heat and it shatters, too little and it never forms at all. If we can crack where and how the universe keeps its fluorine stash, we might unlock secrets about stellar life cycles we've never considered. For now, though, this tiny element remains a colossal puzzle. Whether it's born in the slow breaths of dying stars or the last gasps of exploding ones, one thing's clear: the interstellar medium is holding onto fluorine like a tightly kept secret, and astronomers won't stop digging until they've unearthed the truth. Drifting through the void between galaxies, gigantic clouds of hydrogen move with unnerving speed, some clocking in at over 1 million miles per hour. Astronomers call these enigmatic structures Lyman blotch clouds, named for the telltale ultraviolet glow they emit, and they defy nearly every expectation we have about how gas behaves in the depths of space. Picture a cosmic hurricane, but instead of rain, it's a storm of raw star fuel hydrogen stretching hundreds of thousands of light years, barreling through regions so empty they make our local bubble look crowded. What's so baffling is how these clouds hold themselves together. Normally, gas in intergalactic space should dissipate, scattering like smoke in the wind. Yet these blobs remain shockingly cohesive, their edges sharp as if traced by an invisible hand. Some theories suggest they're tidal debris, the shredded remains of galaxies ripped apart during violent collisions. Imagine two galaxies brushing past each other, their gravitational forces stretching and tearing gas into colossal streamers. Over time, these streamers could clump together, forming the isolated clouds we see today. The problem: many Lyman blotches show no obvious connection to nearby galaxies, leaving no visible crime scene to examine. That's led to a wilder idea. Maybe these aren't wreckage at all, but failed galaxies, dark matter halos that almost became full-fledged galaxies before something went wrong. In the early universe, dark matter's gravitational pull should have gathered enough gas to ignite star formation. But in these cases, something halted the process. Perhaps the gas cooled too slowly, or the dark matter scaffold was too flimsy to hold onto it. The result: a ghostly, starless husk adrift in the cosmic ocean. Survival is the real puzzle. Without the gravitational anchor of stars or dark matter, these clouds should have evaporated eons ago, yet here they are. One clue might lie in magnetic fields, invisible lines of force threading through the gas, acting like a cosmic rubber band to keep it from flying apart. Another possibility involves pressure from the surrounding intergalactic medium, creating a bubble that confines the cloud like a soap film trapping air. The stakes are high because Lyman blotches could be hiding a significant chunk of the universe's missing baryonic matter. If these clouds are as common as some surveys suggest, they might account for a sizable portion of the ordinary matter our models can't currently locate. Future telescopes like the James Webb Space Telescope could finally reveal their origins by peering into their chemical makeup. For now, though, these rogue hydrogen storms remain a cosmic contradiction, too massive to ignore, yet too elusive to fully understand. In the chaotic whirl of interstellar space, where gas swirls at supersonic speeds and temperatures swing from frigid to scorching, one molecule stubbornly defies expectations: CH+ or CH+. On paper, it shouldn't last more than a few seconds. This fragile ion, a simple pairing of carbon and hydrogen missing an electron, is the chemical equivalent of a house of cards in a hurricane. Yet somehow it thrives in some of the most turbulent regions of the galaxy, glowing faintly in infrared light like a cosmic neon sign. How? That's where the mystery deepens. Normally, molecules like CH+ get torn apart almost immediately in harsh environments. Collisions with other particles or even stray photons can break them apart. But in places like the Orion Bar, a violent star-forming ridge bombarded by ultraviolet radiation CH+ appears in shocking abundance. It's like finding delicate ice sculptures standing untouched in the middle of a desert. The leading theory points to rapid chemical reactions sparked by shockwaves. When supersonic gas slams into slower-moving clouds, the energy released can forge CH+ in an instant, like a match struck in the dark. These molecules might only live briefly, but in constantly churning gas, new ones form just as fast as old ones are destroyed, creating an illusion of stability. Then there's the UV radiation paradox. Intense starlight should obliterate CH+, yet in some regions it seems to fuel its creation. Here's the twist: UV photons can strip electrons from carbon atoms, turning them into ions that aggressively bond with hydrogen. It's a bit like lighting a fire by throwing water on it, counterintuitive, but under the right conditions it works. The key might lie in the delicate balance between destruction and renewal. In areas where radiation and turbulence constantly stir the gas, CH+ could be the fleeting byproduct of a never-ending cycle, a cosmic phoenix rising from its own ashes. What makes CH+ so valuable to astronomers isn't just its stubborn existence, it's what it reveals about hidden energy. These molecules act like tracers, marking regions where powerful, unseen forces are at work. When telescopes detect CH+, they're essentially seeing the fingerprints of shockwaves, magnetic fields, or radiation storms that would otherwise be invisible. In the dusty chaos of star-forming clouds where traditional probes fail, CH+ becomes a beacon guiding scientists to the heart of the action. But the plot thickens when you look beyond our galaxy. In distant quasars, billions of light-years away, CH+ has been detected in staggering quantities, far more than local models can explain. Some researchers speculate that supermassive black holes might be driving unimaginable turbulence, creating CH+ on scales we've never witnessed. Others wonder if we're missing a fundamental piece of interstellar chemistry, something that tilts the balance toward this molecule's survival in extreme conditions. For now, CH+ remains both a puzzle and a tool, a fragile clue pointing to the violent, invisible machinery shaping the cosmos. Every new detection challenges our assumptions, reminding us that even the smallest molecules can hold the keys to the universe's biggest secrets. Magnetic fields in space were supposed to follow rules, behaving predictably like giant cosmic weather systems, shaped by the rotation of galaxies and the churning of interstellar gas. But when astronomers started mapping these invisible forces, they found something far stranger: phantom fields threading through the void with a pattern that resembles ordered chaos. Some regions show magnetic lines stretched taut as guitar strings, while others twist into knots tighter than sailor's rope, defying every model of how galactic dynamos should work. Take the famous Musca filament, a towering structure of gas and dust stretching dozens of light-years across our galaxy. Its magnetic field doesn't align with the surrounding galactic plane as expected, but instead runs perpendicular to it like a skyscraper built sideways. Even more bizarre, the field strength fluctuates wildly along its length, with patches of intense magnetism interrupting stretches of eerie calm. It's as if some unseen hand combed through the filament, carefully arranging its magnetic hairs against the galactic wind. Dynamo theories, which explain field generation through the motion of charged particles, can't fully account for this behavior. The fields are too organized, too intentional for simple turbulence to explain. Then there's the cosmic ray conundrum. These high-energy particles, flung across the galaxy by supernova and black holes, should scatter randomly as they encounter interstellar magnetic fields. Instead, they often follow suspiciously straight paths, as if guided by invisible highways. Recent observations with the Fermi Gamma Ray Space Telescope revealed regions where cosmic rays move with uncanny precision along magnetic field lines that by all rights should be tangled beyond recognition. Some researchers speculate these phantom fields might act like cosmic fiber optics, channeling particles over vast distances with minimal resistance. Others propose the fields are far more rigid than we thought, resisting distortion like steel cables in a rubber universe. The real puzzle lies in the field's persistence. Magnetic fields should decay over time, their energy dissipating like heat from a dying ember. Yet many interstellar fields appear ancient, older than the stars they weave between. One radical idea suggests these fields are primordial, fossils from the early universe when space itself crackled with electromagnetic energy. If true, they'd be relics of a time before galaxies formed, preserved in the interstellar medium like insects in amber. Another theory points to dark matter, proposing that interactions with these invisible particles might subtly reinforce magnetic structures, preventing their collapse. What's clear is that these phantom fields are more than cosmic curiosities, they're puppeteers, quietly shaping everything from star formation to the trajectories of high-energy particles. If our models are missing a fundamental piece of magnetism's role in the cosmos, it could rewrite how we understand the forces stitching the universe together. Until then, these orderly yet chaotic field lines remain one of the interstellar medium's most elegant enigmas, a reminder that even in the void, there's a hidden architecture we're only beginning to trace. The universe's periodic table has a glaring blank spot. Where are all the heavyweights, elements like uranium, thorium, and plutonium, collectively known as actinides, should be floating through the interstellar medium in detectable amounts? They are forged in the most violent stellar explosions, from neutron star collisions to rare supernovae, and yet when astronomers scan the cosmos for their spectral signatures, they come up nearly empty-handed. It's as if the universe has a hidden vault, locking away these radioactive treasures where we can't see them. One clue might lie in interstellar dust. Actinides are notoriously clingy. Their electrons arrange themselves in ways that make them bond easily with other elements, particularly oxygen and carbon. In the cold depths of space, they could be hitching rides on dust grains, coating them like radioactive frost. These grains might then clump together, forming microscopic hiding places too diffuse to detect with current telescopes. Imagine searching for a needle in a haystack, only to realize the needle has been pulverized and sprinkled evenly across a field. That's the scale of the challenge here. But there's a twist. Some actinides might not be hiding at all. They could have been thrown out of the galaxy entirely. Rare supernovae, like magneto-rotational hypernova, unleash such ferocious energy that they might catapult heavy elements far beyond their host galaxies, strewing them into the intergalactic void like cosmic shrapnel. If true, this would mean our inventories of galactic chemistry are fundamentally incomplete, missing elements that were literally blasted off the map. Then there's the timing problem. Actinides decay over time, and many have half-lives shorter than the age of the Milky Way. Could it be that most of what was created early in the universe's history has simply vanished, leaving behind only faint traces? It's like trying to reconstruct a fossil record when 90% of the bones have turned to dust. Perhaps the most tantalizing possibility is that we're not looking in the right way. Actinides absorb and emit light at very specific wavelengths, often in the ultraviolet or X-ray range, frequencies that Earth's atmosphere blocks. Space telescopes like Chandra and Hubble have spotted hints of uranium in a handful of distant gas clouds, but these detections are whisper-thin, leaving room for doubt. Future observatories like the European Space Agency's Athena mission might finally crack the case by peering deeper into the X-ray spectrum. What's at stake isn't just a bookkeeping exercise. Actinides are cosmic clocks. Their decay rates help us date events like supernova and even estimate the age of the Milky Way. If they're missing or misplaced, our understanding of galactic history might be built on shaky foundations. Until we solve this elemental vanishing act, the interstellar medium's chemical ledger will remain unbalanced, a mystery written in the faint, radioactive ink of the cosmos. Buried within the static of the cosmos, there's a sound, a faint, whispering hiss that blankets the Milky Way. This isn't the crackle of distant stars or the pop of exploding supernova. It's something far more elusive, an all-pervasive radio hum, the kind you'd hear if you tuned an old-fashioned receiver between stations. Astronomers call it the synchrotron background, and while they've known about it for decades, its origins remain one of the galaxy's most stubborn enigmas. On the surface, the explanation seems straightforward. Synchrotron radiation occurs when high-speed electrons spiral around magnetic field lines, releasing energy as radio waves. It's a well-understood process responsible for the glowing trails of particle accelerators and the eerie light of pulsar wind nebulae. But the Milky Way's radio hiss doesn't behave like it should. Instead of a uniform glow, it flickers unpredictably brighter in some regions, eerily muted in others, as if someone's turning an invisible dial up and down across the galaxy. Take the galactic center, for instance. Near Sagittarius, a star, the supermassive black hole anchoring our galaxy, the hiss swells to a roar, drowning out nearly everything else. Yet just a few thousand light-years away, in the so-called radio-quiet zones, the signal dips to near silence. Even stranger, the hiss's intensity shifts with frequency in ways that defy standard synchrotron models. At lower frequencies, it's louder than predicted. At higher ones, it fades too quickly, like a voice that cracks mid-sentence. One theory blames cosmic rays, high-energy particles zipping through space. When these particles collide with interstellar gas, they could produce secondary electrons that amplify the radio noise. But here's the catch. The distribution of cosmic rays we've mapped doesn't fully account for the hiss's erratic patterns. It's as if there's an unseen population of particles lurking just beyond our detection, stirring up the signal like ghostly conductors. Then there's the dark matter angle. Some researchers propose that hypothetical particles like weakly interacting massive particles, WIMP, could decay or annihilate, releasing electrons that contribute to the synchrotron glow. If true, this hiss might be the closest thing we have to hearing dark matter, but without definitive proof, it remains a tantalizing what if. The most puzzling aspect might be the hiss's ubiquity. Unlike other cosmic signals which fade in and out as you scan the sky, this one lingers everywhere like static on an old TV screen. That suggests it's not tied to any single source, not supernova, not black holes, not even the galaxy's spiral arms. Instead, it seems woven into the fabric of the interstellar medium itself, a product of countless subtle interactions we've yet to unravel. What's at stake isn't just academic curiosity. This radio whisper could be a signpost for processes we've overlooked: hidden particle accelerators, undiscovered magnetic phenomena, or even physics beyond our current models. Future telescopes like the Square Kilometre Array aim to dissect the hiss with unprecedented precision, peeling back its layers like an onion. Until then, it remains a cosmic white noise machine, playing a tune we're only beginning to decipher. Hurtling toward the Milky Way at nearly 200 miles per second, the Smith cloud stretches like a colossal, ghostly hand reaching across the void, a river of gas 11,000 light-years long and 2,500 light-years wide, holding enough hydrogen to forge 2 million suns. Discovered in the 1960s by astronomy student Gail Smith, this cosmic streamer shouldn't exist. By all rights, it should have disintegrated eons ago, torn apart by galactic tides or vaporized by the searing heat of intergalactic space. Yet here it is, intact and barreling toward us, leaving astronomers divided over whether it's a fragment of a devoured dwarf galaxy or a belched-out piece of our own Milky Way. The extragalactic camp points to the cloud's trajectory. Unlike most galactic gas clouds which orbit in sync with the Milky Way's rotation, the Smith cloud rockets in at a steep, retrograde angle, like a car merging onto a highway in the wrong direction. Its composition fuels the mystery. Sulfur levels match those found in the outer fringes of dwarf galaxies, suggesting it might be the tattered remains of a smaller system shredded by our galaxy's gravity. If true, the cloud is a fossil, a silent witness to the Milky Way's cannibalistic past. Yet there's a problem with this theory. The cloud's structure is too coherent. Galactic tides should have stretched it into incoherent streams like taffy pulled too thin. That's why others argue for a homegrown origin. Maybe the Smith cloud was ejected from the Milky Way's disk by a chain of supernova explosions millions of years ago, a cosmic sneeze powerful enough to launch gas clear out of the galactic plane. Simulations show that such galactic fountains can occur, with expelled gas eventually raining back down. But this, too, has inconsistencies. The cloud's velocity is suspiciously high for a mere supernova kick, and its lack of heavy elements contradicts expectations for material forged in the star-rich galactic disk. The real enigma lies in its survival. Intergalactic space is a brutal environment, and gas clouds are fragile. Without some invisible scaffold, the Smith cloud should have evaporated long ago. Some researchers suspect magnetic fields might be acting like cosmic duct tape, holding it together against all odds. Others propose dark matter. If the cloud is indeed extragalactic, it might be trailing a faint halo of this mysterious substance, its gravity providing the cohesion we observe. What's certain is that the Smith cloud is more than a curiosity. It's a test case for how galaxies grow and recycle their material. In about 30 million years, it will slam into the Milky Way's disk near the Perseus spiral arm, potentially igniting a firestorm of star formation. Until then, it remains a celestial riddle, a ghostly fingerprint pressed against our galaxy's edge, challenging us to decipher whether it's the last gasp of an alien world or a piece of our own cosmic home, flung outward only to return like a boomerang in the night. Space isn't just cold, it's brutally cold, with most of the interstellar medium hovering just a few degrees above absolute zero. But scattered through this frozen void are pockets of gas so hot they glow with temperatures in the millions of degrees. It's like finding a boiling teapot in the middle of Antarctica, a paradox that defies everything we know about how heat behaves in a near-perfect vacuum. These blistering bubbles, detected by their faint X-ray emissions, shouldn't exist, yet they do, clustered in regions where logic says they'd cool and vanish in an instant. The leading suspect, supernova shockwaves. When a massive star explodes, it doesn't just vanish, it sends ripples of energy tearing through space at thousands of miles per second. These shock fronts act like cosmic blowtorches, supercharging any gas they encounter. But here's the catch. Simulations show these heated regions should dissipate within millennia, their energy bleeding into the surrounding void. Instead, we see pockets that persist for millions of years, glowing stubbornly in places where no supernova has erupted in eons. Some researchers argue that multiple overlapping shocks could keep reheating the gas, like a pot repeatedly brought back to a boil. Others point to turbulent echoes and energy ricocheting off denser clouds, trapping heat in isolated bubbles far from the original blast. Then there's the magnetic wildcard. Space isn't truly empty, it's threaded with invisible magnetic fields, and when these lines snap and reconnect, they unleash staggering bursts of energy. This process, called magnetic reconnection, is the same phenomenon that triggers solar flares on the Sun. In the interstellar medium, however, it might operate on scales we're only beginning to grasp. Picture a tangled net of rubber bands suddenly releasing their tension. The snap could heat nearby gas to extreme temperatures without any visible explosion. Observations of the North Polar Spur, a vast arc of hot gas stretching over the Milky Way, hint at this possibility. Its structure aligns eerily with predicted magnetic reconnection sites, as if the galaxy itself is running a hidden electrical grid. But the real enigma is containment. How does gas this hot not just blast itself apart? In Earth's atmosphere, heat spreads through collisions between molecules, but in space, particles are so sparse they might collide only once every century. One theory suggests magnetic fields act like insulation, wrapping the hot gas in a shimmering force field that slows energy loss. Another idea involves cosmic rays. High-energy particles buzzing through the medium might inject just enough energy to keep the gas simmering. Perhaps the most baffling cases are the isolated pockets far from any obvious energy source. In the constellation Ursa Major, X-ray telescopes have spotted a glowing cloud with no nearby supernova remnants or young stars to explain its heat. Could there be invisible processes at work, dark matter annihilation, or quantum effects we've yet to discover? Or are we seeing the aftermath of events so ancient their triggers have long since faded from view? What's clear is that these hot islands in a cold sea aren't just cosmic oddities, they're clues. If supernova alone can't explain them, our models of galactic energy cycles are missing a critical piece. And if magnetic fields play a larger role than we thought, the interstellar medium might be far more electrically active than we ever imagined. Until we solve this thermal riddle, the universe's pockets of million-degree gas will keep burning with questions outliers in the cold, dark vastness of space. Deep in the darkest corners of interstellar space, where starlight barely reaches, astronomers have detected an eerie blue glow, soft, diffuse, and utterly puzzling. This isn't the familiar shimmer of starlight scattering through gas or the fiery hues of distant nebulae. It's something far stranger, a faint cerulean light that clings to specific patches of the sky like cosmic graffiti sprayed across the void. The leading suspect, microscopic diamonds spinning so fast they glow. These aren't the gemstones you'd find in a jewelry store. They're nanodiamonds, tiny carbon crystals no larger than a virus, forged in the violent deaths of ancient stars or the shockwaves of supernova. When these minuscule structures are zapped by starlight, they don't just sit there. They begin to pirouette, their surfaces vibrating at mind-bending speeds. That motion generates a peculiar kind of radiation, emitting light skewed toward the blue end of the spectrum. It's a phenomenon called spinning dust emission, and it might explain why certain blackened regions of space emit this ghostly azure light. But here's where things get weird. This blue glow isn't everywhere. It clusters in specific directions, avoiding vast swaths of the galaxy as if following some hidden cosmic blueprint. The Taurus molecular cloud, for instance, shows a strong signal, while neighboring clouds of similar composition remain conspicuously dark. Even more baffling, some regions with dense carbon-rich gas where nanodiamonds should thrive don't exhibit the glow at all. It's as if an unseen switch flips the light on or off depending on location. One theory points to magnetic fields. Nanodiamonds carry a slight electric charge, making them sensitive to magnetic forces. In areas where fields are strong and orderly, they might align like compass needles, spinning in unison and amplifying the blue glow. Elsewhere, chaotic fields could send them tumbling randomly, canceling out the effect. Another idea involves radiation intensity. Too much ultraviolet light might overcharge the diamonds, causing them to spin too fast and emit at wavelengths we can't detect. Then there's the chemistry angle. Not all interstellar carbon forms nanodiamonds. Most of it exists as soot-like grains or sprawling molecules. The blue glow's patchiness might reflect a hidden cosmic recipe-specific conditions where carbon atoms assemble into diamonds rather than other structures. Certain star-forming regions, rich in shockwaves and turbulence, could act as diamond factories, while calmer areas produce only cosmic charcoal. The implications stretch beyond mere curiosity. If this light truly comes from nanodiamonds, it would mean the galaxy is littered with them, countless trillions of microscopic gems adrift in the darkness. More tantalizingly, their uneven distribution could map out hidden processes in the interstellar medium, revealing how carbon, the backbone of life, cycles through the cosmos. Future telescopes, like the upcoming James Webb Space Telescope, might finally pinpoint the glow's origins by analyzing its spectral fingerprints with unprecedented precision. Until then, this ethereal blue light remains a cosmic cipher, a whisper from the darkness hinting at unseen structures and untold stories written in carbon. Whether it's spun from diamonds or something even more exotic, one thing's clear: the universe has a flair for the mysterious, painting its secrets in hues we're only beginning to perceive. Rivers of glowing hydrogen snake through galaxies like luminous veins, carrying the raw fuel for star birth across unimaginable distances. These aren't calm, meandering streams. They're raging torrents of ionized gas, superheated to tens of thousands of degrees and stretching tens of thousands of light years. Astronomers call them H2 regions, where ultraviolet radiation from young stars strips hydrogen atoms of their electrons, causing them to emit that characteristic pinkish-red glow visible in nebulas like Orion. But here's the cosmic conundrum. Some of these rivers flow uphill, seemingly defying gravity's pull as they channel gas into regions where star formation shouldn't be possible. Take the Magellanic Stream, a colossal ribbon of gas arcing around our Milky Way. This structure, torn from the small and large Magellanic Clouds by tidal forces, should be crumbling under our galaxy's gravitational might. Instead, parts of it shine with unexpected H2 emissions, particularly in a region called the Leading Arm. These glowing patches indicate active star formation, except there's no dense molecular gas nearby to fuel it. One daring theory suggests cosmic rays or shocks from the Milky Way's halo might be reionizing the gas, effectively jump-starting stellar nurseries in the void. It's like finding lush gardens blooming in the middle of a desert, fed by some hidden underground spring we can't see. Then there's the mystery of the orphan H2 regions. In galaxies like Messier 83, astronomers have spotted luminous pockets of ionized hydrogen completely untethered from any visible star clusters. Normally, massive young stars provide the UV radiation that makes hydrogen glow, but in these cases, the usual suspects are missing. Some researchers speculate that runaway stars might be the culprits, blazing through space so fast they've left their birth clouds behind while still ionizing new ones along their path. Others propose an even wilder idea, that dark matter interactions could be generating enough localized heat to ionize the gas without any stars involved at all. The real game changer lies in how these rivers shape galactic evolution. Computer simulations show that when H2 streams collide, they create turbulence, chaotic motions that actually help gas cool and condense into new stars. This turns conventional wisdom on its head, where turbulence was thought to prevent star formation by keeping gas too stirred up to collapse. Now we're seeing evidence that at certain scales, it might do the opposite, acting like a cosmic whisk that whips interstellar ingredients into stellar recipes. The antennae galaxies, locked in a violent merger, showcase this perfectly. Their colliding rivers of ionized hydrogen have birthed spectacular superstar clusters, each containing millions of young suns. What makes these cosmic rivers so fascinating is their unpredictability. Some, like the Fermi bubble's glowing edges, trace the aftermath of ancient cataclysms. Others, like the mysterious filaments in the Cygnus X region, seem to emerge from nowhere, their ionizing sources hidden behind thick dust clouds. As new telescopes like the James Webb Space Telescope peer deeper into these luminous networks, we're realizing they're not just incidental features, they're the circulatory system of galaxies, pumping life-giving gas to where it's needed most, often following rules we're only beginning to decipher. Every glowing filament, every rogue H2 region is a clue, and the universe has left them scattered across the sky like pieces of a puzzle we've barely started assembling. Scattered across the galaxy like cosmic craters, superbubbles are the aftermath of stellar demolition derbies, colossal cavities carved out by the combined fury of dozens of supernovae and the relentless winds of massive stars. These structures should be expanding at breakneck speeds, their shockwaves rippling through the interstellar medium at thousands of miles per second. Yet when astronomers clock their growth, many move with an almost deliberate slowness, as if something invisible is pressing back against them. It's like watching a balloon inflate underwater, its edges meeting resistance no one can see. Take the Orion Eridanus superbubble, a sprawling void over 1,500 light-years wide. Born from the fury of the Orion OB1 association, a gang of young, volatile stars, its shock front should have raced outward, shredding surrounding gas clouds. Instead, its edges advance at a fraction of the predicted speed, as though snagged on cosmic Velcro. One explanation lurks in the realm of dark matter. While this mysterious substance rarely interacts with ordinary gas, some models suggest dense halos of it might cluster around star-forming regions, their gravitational grip subtly breaking the bubble's expansion. Imagine rolling a bowling ball through a field of molasses. You wouldn't see the syrup, but you'd feel the drag. Then there's the magnetic stranglehold theory. The interstellar medium isn't just gas, it's laced with magnetic fields, and these invisible lines of force can behave like elastic bands. When a superbubble's shockwave plows into them, they might stretch and recoil, sapping energy from the expansion. Observations of the GUM Nebula support this. Its western rim shows magnetic fields coiled into tight spirals, as if they've been wound like springs by the bubble's advance. In some regions, the field strength measures 50 times the galactic average, enough to cage even the most violent stellar outbursts. But the real puzzle lies in the outliers, bubbles that aren't just slow but asymmetric. The Cygnus superbubble, for instance, bulges dramatically toward Earth while its far side remains oddly stunted. One side might be pressing against a hidden wall of dense gas, while the other spills into a rarefied tunnel carved by ancient supernovae. Or perhaps we're seeing the fingerprints of galactic spiral arms, their gravitational tides warping the bubbles like hands squeezing a stress ball. What makes these restrained explosions so critical is their role as galactic sculptors. By regulating how energy disperses, they determine where future stars can and can't form. Slow-moving superbubbles might act like cosmic dams, corralling gas into dense pockets ripe for star birth. Others could stifle stellar nurseries entirely, their languid expansion leaving too much turbulence in their wake for gravity to gather material. This delicate balance between chaos and order might hold the key to why some galaxies blaze with star formation while others fade into quiet middle age. Yet for all their influence, superbubbles remain eerily silent in one crucial way. They emit almost no radio waves. Most high-energy structures in space crackle with synchrotron radiation, but these cavities stay stubbornly mute. Some astronomers suspect their magnetic fields might be trapping particles too efficiently, preventing the electron acceleration that produces radio noise. Others wonder if the particles themselves are different, maybe richer in heavy elements that cool too quickly to radiate. Every new observation peels back another layer of the mystery. Are these bubbles being restrained by dark matter's ghostly grip, or are magnetic fields the unseen architects of their sluggish growth? Perhaps it's both, a cosmic tug of war where invisible forces shape the visible universe in ways we're only beginning to glimpse. One thing's certain, the longer we stare into these silent expansions, the more they whisper that our maps of galactic ecology are missing entire dimensions. Threading through the galaxy like cosmic scaffolding, the so-called bones of the Milky Way are some of the most striking and puzzling structures in the interstellar medium. These dense, slender filaments stretch hundreds of light-years along the spiral arms, acting as the skeletal framework upon which star formation hangs. Unlike the chaotic swirls of gas and dust surrounding them, these bones are eerily uniform, each measuring roughly 50 light-years across, as if the universe drafted them using a cosmic ruler. What's baffling isn't just their precision, but their resilience. Spiral arms are battlegrounds of turbulence, where shockwaves from supernova and stellar winds rip through gas clouds, shredding them into clumps. Yet these bones remain steadfast, resisting fragmentation as if held together by some invisible glue. Take the Nessie bone, a sinuous structure threading through the scutum Centaurus arm. Despite sitting in one of the galaxy's most violent stellar nurseries, it's remained coherent for millions of years, defying simulations that predict such filaments should dissolve into blobs within millennia. One clue lies in their magnetic spines. Observations reveal these bones are laced with powerful magnetic fields, running parallel to their lengths like iron rods reinforcing concrete. These fields might act like cosmic zippers, suppressing turbulence and preventing the gas from splintering. Picture a tightrope walker balancing in a hurricane. The rope's tension keeps them steady despite the chaos. Similarly, magnetic tension could be the secret to these filaments' unnatural stability. Then there's the gravity factor. Bones are denser than their surroundings, packing enough mass to exert a strong gravitational pull on themselves. This self-attraction might counteract disruptive forces, creating a delicate equilibrium where gas neither collapses into stars nor scatters into the void. But here's the catch: gravity alone can't explain their uniformity. Why don't we see bones of all sizes, from shoelace-thin strands to colossal pillars? Some theorists point to the sonic scale, a cosmic speed limit set by the speed of sound in interstellar gas. Below this threshold, pressure waves can't propagate fast enough to fragment the filament, leaving bones forever stuck at the same characteristic width. The biggest enigma might be their role in galactic ecology. These filaments aren't just passive backdrops, they're stellar assembly lines. Stars tend to form along their lengths like pearls on a string, suggesting bones funnel gas efficiently into nurseries. But how? One provocative idea involves gravitational leakage. As gas slides along a bone's magnetic highways, slight density fluctuations might trigger localized collapses, seeding stars without destroying the filament. It's a self-regulating system where star birth siphons just enough material to keep the structure intact while replenishing it with fresh gas from the spiral arm's rotation. Yet mysteries linger. Why do bones avoid certain spiral arms entirely? And what explains the occasional knotted segments, regions where these filaments balloon with star formation before snapping back to their slender forms? Some hidden interplay of forces, perhaps involving dark matter or unseen stellar feedback, might be pulling the strings. Until we unravel these threads, the bones of our galaxy will remain both map and riddle, outlining the Milky Way's anatomy while guarding the secrets of its growth. Deep in the frozen outskirts of molecular clouds, where temperatures plunge close to absolute zero, dust grains become cosmic snowballs, their surfaces cloaked in icy mantles of water, carbon monoxide, and methane. These icy coatings are interstellar laboratories, birthing complex molecules through chemistry that would freeze in place anywhere else. Yet when scientists tally up the expected ingredients, one element keeps vanishing: oxygen. It's the universe's third most abundant element, so where is it hiding in these cosmic ice rinks? One clue lies in the ice's composition. Observations from telescopes like the Atacama Large Millimeter Array reveal a glaring mismatch. Water ice oxygen bound to hydrogen shows up in expected amounts, but other oxygen-rich molecules like carbon dioxide and methanol are suspiciously scarce. It's as if someone snipped every second oxygen atom from the recipe. Some researchers blame ultraviolet radiation, which bombards these grains like a cosmic sandblaster. UV photons can break apart molecules, liberating oxygen atoms to escape into space or recombine into forms our telescopes can't easily detect. Imagine blowing on a dandelion. The seeds oxygen scatter, leaving the stem hydrogen and carbon behind. But UV radiation might not be the only thief. Laboratory experiments suggest another culprit: amorphous ice. Unlike the orderly crystalline ice in your freezer, interstellar ice is messy, its molecules arranged haphazardly. In this jumbled state, oxygen could be locked away in exotic molecular cages, structures like clathrates, where gas molecules nestle inside ice lattices. These traps might sequester oxygen in forms invisible to current telescopes, like a key stashed in a drawer no one's thought to open. Then there's the silicate conspiracy. Dust grains at the ice's core are often rich in silicates, minerals packed with oxygen. Under the right conditions, this solid phase oxygen might slowly leach into the ice, bonding with other elements in ways that don't produce familiar spectral signatures. Picture a sponge soaking up water. The moisture is there, just not in a form you can pour out. The stakes are higher than they seem. Oxygen's disappearance skews astrochemical models which predict how molecules form in space. If we can't account for it, our understanding of interstellar chemistry, and by extension, the building blocks of planets and life, rests on shaky foundations. Future missions like NASA's James Webb Space Telescope may finally track down these missing oxygen reservoirs, peering into icy grains with infrared eyes sharp enough to spot hidden molecular vaults. Until then, the case of the vanishing oxygen remains a chilly enigma, a reminder that even the most abundant elements can slip through the cracks of our cosmic awareness. For over a century, those cryptic dark lines in starlight, the diffuse interstellar bands have taunted astronomers like a cipher without a key. But recent breakthroughs are cracking the code wide open, revealing hints of molecular giants lurking in the cosmic shadows. The latest spectral data points to structures far more complex than anyone imagined. Sprawling carbon frameworks dozens of atoms wide, fluttering through space like microscopic kites in a stellar wind. Some researchers argue these could be probiotic seeds, the very precursors to life itself, while others suspect we're glimpsing an entirely new branch of interstellar chemistry. Take the so-called C60 solution, the idea that Buckminster fullerene, a soccer ball-shaped molecule of 60 carbon atoms, might explain certain DIBs. When scientists shot infrared lasers at these lab-made buckyballs, the resulting spectra aligned suspiciously well with unexplained interstellar absorption lines. Even more compelling, NASA's Spitzer Space Telescope detected C60's infrared signature in planetary nebulae, proving such molecules can survive in space. But here's the twist: buckyballs only account for a handful of the hundreds of known DIBs. The rest demand even larger, more intricate architectures, molecular skyscrapers that push the limits of known chemistry. That's where polycyclic aromatic hydrocarbons (PAR) enter the debate. These flat, chicken wire sheets of carbon and hydrogen are interstellar veterans, found everywhere from comet tails to star-forming clouds. Under the right conditions, they can stack or curl into complex 3D forms, potentially explaining broader DIB patterns. Yet lab tests reveal a glaring mismatch. While PAHs absorb light at the right wavelengths, their spectral fingerprints lack the precise sharpness seen in space. It's as if nature is using similar building blocks but assembling them in ways our labs haven't replicated. The plot thickens with the discovery of carriers that defy conventional categories. Certain DIBs show bizarre substructure, tiny absorption spikes within broader bands, hinting that their molecular hosts might be flexing or spinning as they drift through magnetic fields. Imagine a tumbling gymnast whose movements subtly alter their silhouette against light. One radical theory suggests these could be carbon nanotubes, hollow cylinders with quantum properties that shift depending on their orientation. Another posits graphene oxides, oxidized sheets of carbon that fold and flutter like cosmic origami. Then comes the most tantalizing question: could these molecules be life's interstellar messengers? In the Orion molecular cloud, DIB intensities spike near regions rich in organic compounds, fueling speculation they might be delivering probiotic material to young planetary systems. But skeptics counter that most DIB carriers appear too stable and inert to react into life's precursor molecules. Instead, they might represent a cosmic reservoir, a dead-end molecular relics that accumulate over eons without participating in biochemistry. New telescopes like Webb are bringing this mystery into sharp focus. By analyzing how DIBs vary across different environments, from the harsh ultraviolet glare near young stars to the frigid quiet of dark clouds, we're finally mapping the conditions that birth and sustain these enigmatic molecules. Each observation peels back another layer, revealing not just answers but deeper questions about how complexity emerges in the void. Whether they're life's starting blocks or nature's exotic art forms, one thing's clear: these phantom molecules are rewriting the rules of cosmic chemistry before our eyes. Galaxies breathe inhaling gas to birth stars, exhaling torrents of superheated wind when those stars die. But astronomers are realizing these cosmic gusts aren't blowing as hard as they should. According to simulations, star-forming galaxies like the Milky Way should be generating galactic winds powerful enough to strip away their own gas reservoirs within a billion years, effectively starving themselves into a quiet retirement. Yet when telescopes measure actual outflows, they find winds moving at half the predicted speed, too feeble to explain why galaxies aren't still churning out stars at breakneck rates. It's as if the universe has a hidden braking system, silently tempering these outflows, and the hunt for its identity is uncovering forces we never knew existed. Take starburst galaxies' cosmic fireworks displays where stars form hundreds of times faster than in our Milky Way. These systems should be the ultimate wind machines, their supernova and stellar winds combining into a hurricane-force exhalation. Yet observations of galaxies like Messier 82 reveal winds that, while impressive, lack the punch to match theoretical expectations. The discrepancy is stark. Models predict gas should be ejected at thousands of kilometers per second, but most outflows barely crack 800. One clue might lie in the wind's structure. Instead of a smooth, unimpeded flow, they're clumpy and fragmented, like smoke from a flickering candle. This suggests the interstellar medium itself is fighting back, with dense gas clouds acting like speed bumps, sapping momentum from the outflow. Dark matter might be the silent moderator. Most galaxies are cocooned in sprawling halos of this mysterious substance, and while it doesn't interact with ordinary matter directly, its gravity could subtly reshape how winds propagate. Picture a river flowing downhill. If the slope suddenly levels out, the current slows. Similarly, dark matter's gravitational pull might create an unseen plateau in galactic outflows, preventing them from accelerating to their full potential. The Phoenix cluster offers a tantalizing hint. Its central galaxy's outflow slows abruptly at the exact radius where dark matter models predict its halo's density should peak. Then there's the magnetic wildcard. Galactic winds aren't just gas, they're laced with magnetic fields, and these invisible lines of force might act like interstellar rains. In the nearby galaxy NGC 624, radio telescopes have detected magnetic fields coiled tightly around outflow channels, as if the wind is being funneled through cosmic straws. This could explain why some outflows appear collimated, jetting outward in narrow streams rather than spreading diffusely. By channeling the energy into focused beams, galaxies might lose less wind overall, preserving their gas reserves far longer than simulations anticipate. The stakes couldn't be higher. If we're missing a fundamental piece of how galactic winds operate, our entire understanding of galaxy evolution might need recalibrating. Slow outflows could solve another cosmological puzzle: why the universe hasn't burned through its star-forming fuel already. Perhaps these tempered winds are the universe's failsafe, a built-in governor preventing galaxies from exhausting themselves too quickly. Future telescopes like the 30-meter telescope aim to probe wind dynamics in unprecedented detail, peeling back the layers of this cosmic throttle. Until then, the great galactic wind discrepancy stands as a humbling reminder. Even the mightiest forces in the universe might be moving to rhythms we're only beginning to sense. From the ghostly whispers of hydrogen walls to the defiant heat of million-degree gas bubbles, these 30 mysteries aren't just cosmic curiosities. They're proof that the interstellar medium is anything but empty. It's a dynamic, living frontier where magnetic fields sculpt invisible architectures, where dark gas hides in plain sight, and where fragile molecules thrive against all odds. Every discovery peels back another layer, revealing just how much we've underestimated the chaos and the order lurking between the stars. Take the enigma of galactic fountains, where galaxies exhale storms of star fuel only to recapture it like cosmic breath. Or the silent defiance of fluorine, a rebellious element that refuses to follow the rules of stellar chemistry. Even the simplest things, like why some interstellar dust glows blue or where half the universe's lithium vanished, turn out to be anything but simple. These aren't gaps in our knowledge, they're neon signs pointing to entire chapters of physics we've yet to read, and the tools to read them are coming. The James Webb Space Telescope, with its infrared eyes, is already unraveling the secrets of dark molecular clouds and those elusive diffuse interstellar bands. The square-kilometer array, poised to scan the sky with unmatched precision, might finally trace the hidden rivers of dark gas or decode the synchrotron hum that blankets the galaxy. Even ESA's Athena mission could spot the X-ray whispers of missing actinides, those radioactive ghosts we've chased for decades. But here's the beautiful paradox: the more we uncover, the more the universe reminds us how small we are. We're cosmic detectives piecing together a puzzle where half the pieces are still hidden, and the picture keeps changing. Those flickering polarizations in starlight, the rogue hydrogen clouds barreling toward us, the diamonds spinning in the void, they're not just mysteries. They're invitations to stay curious, to wonder. So tell us, which of these interstellar riddles keeps you up at night? Is it the phantom magnetic fields, the missing baryons, or something else entirely? Drop your favorite in the comments, because the universe isn't done surprising us, and neither are we. The next breakthrough might not just rewrite a textbook, it might redefine our place in the grand, mysterious tapestry of space. And that's a story we're all part of.